Good morning, everyone. Today we're going to walk through flexural strength testing of concrete, specifically the method using a simple beam with third-point loading. Now, I want you to look at this diagram carefully. You see the beam sitting on two support blocks, and you see two loading points on top. That's what makes this third-point loading. We're not applying the load in one spot. We're applying it at 2 points, evenly spaced, so we create a constant moment region in the middle of the beam. Why do we do this test? Because flexural strength, also called the modulus of rupture, helps us understand how concrete performs in bending, like what happens in slabs, pavements, and beams when traffic or loads cause the concrete to flex. In the lab, this is not a push until it breaks test. This is a precision test. Small mistakes in alignment, gaps in dimensions can give you the wrong strength. So our focus today is accuracy, consistency, and repeatability. All right, team. Before we touch the machine, let's understand the mission. This method determines the flexural strength, the modulus of rupture of concrete specimens. The procedure here is based on a simple beam test with third-point loading. Now look at the diagram on the left. We have supports at the ends, we have two loads applied at the third points, and the beam fails in bending, typically in the middle region. Now the right side is extremely important. These are critical constraints. First constraint: unit systems. This deck reminds us that values may be shown in SI or inch-pound units, but we must not mix them. Mixing units is one of the easiest ways to create reporting errors. Second constraint: safety. This overview is technical methodology only. In the lab, you must establish safe practices. Wear PPE. Keep hands clear of moving parts. Be cautious with fractured specimens because broken edges are sharp, and never stand in the line of potential debris when the beam snaps. So the goal is clear. Measure flexural strength correctly and safely, using the correct system of units and correct procedures. Now let's talk about the machine itself. Because if the machine doesn't meet the requirements, your test results don't mean anything. Loading mechanism. The machine must provide continuous loading in one stroke. That means we don't want stop-and-go loading. No hesitation, no jerky movement. It also says hand-operated pumps are permitted only if they have enough volume for a single continuous stroke. In plain terms, you can't be pumping and pausing and pumping again, because that creates shock loading or interruptions. Data capture. The machine must record or hold the peak load, and it needs to be accurate within 1%. That means if you're using a digital machine, you must confirm the display is working properly. If you're using an analog system, you must make sure the peak indicator is functional. Verification. Force verification is mandatory. In lab terms, your load cell calibration and verification must be current. So, technicians, always remember, even if your specimen is perfect, if your machine is not verified and your loading isn't smooth, the test is compromised. Now, this slide is where technicians either get it right or lose the whole test. We're looking at loading geometry and alignment. Notice the beam sits on two supports. The span length is labeled L, and the load points are placed at L/3 from each support. That's why we call it third-point loading. You'll also see the note about optional positions for one steel ball and one steel rod. That's part of how the loading blocks allow proper seating and slight rotation so the load is distributed properly. Now pay attention to the bottom notes. Alignment. Forces must be applied perpendicular to the face without eccentricity. That means the load must be centered, no sideways push, no tilt. Precision. Maintain span length and block distance constant within plus or minus 1.0 millimeter. That's a very tight tolerance, so yes, your setup matters. Critical ratio. The ratio of horizontal distance, load to reaction, to beam depth must be 1.0 plus or minus 0.03. That means geometry matters relative to beam size. Technicians, this is why we don't rush setup. If the beam isn't properly aligned, you can cause torsion or uneven stress, and the beam will fail incorrectly. Let's focus on the bearing blocks. These blocks are not just accessories, they are part of the test accuracy. This diagram shows the bearing block with a steel roller, a pivot point, spring-loaded screws, and a loading block plate. Now the key specs here. Maximum height, less than or equal to 65 millimeters, measured from the pivot center. This controls the geometry so the load application stays correct. Width must extend across the full width of the specimen. If the bearing block is too narrow, you'll create concentrated stress and false results. Surface plainness. Deviation less than or equal to 0.05 millimeters. This is critical. If the surface isn't flat, you'll have point contact and uneven loading. Pivot mechanics. The block must remain vertical using spring-loaded screws, and the curved surface angles are specified so it can rotate properly without binding. In simple lab language, the blocks must be clean, flat, properly seated, and functioning smoothly. Otherwise, your beam won't load evenly. Now, let's talk about the specimen, the beam itself. This slide shows the beam with right angles, and the note that the test span is typically about 3 times the depth, within a tolerance. Now look at the bottom requirements. Surface quality. All surfaces must be smooth and free of scars, indentations, holes, or inscribed marks. Technicians. If someone wrote directly into the beam, scratched it, chipped an edge, or damaged the tension face, that beam is not ideal for testing. Compliance. Specimens must be prepared and cured according to applicable laboratory or field practice standards. In real terms, your curing method matters. Your storage matters. Your moisture condition matters. If curing is inconsistent, strength results become inconsistent. So your job is not just to break the beam, it's to protect the specimen integrity from casting through testing. This slide is the technician's discipline slide. Preparation and handling. Timing and moisture. Test immediately upon removal from moist storage. Keep the beam moist until testing. Why? Because surface drying can reduce measured strength. A dry surface changes the stress distribution and can cause microcracking. Orientation. Turn the specimen on its side relative to the molded position. And for sawed specimens, the tension face corresponds to the top or bottom of the cut. What does that mean in practice? You need to know which face was originally finished and which face should be in tension during testing. Centering. Center the specimen on the support blocks. Technicians, centering is not close enough. It needs to be properly positioned so your span is correct and your loading points land where they should. A small offset can change the failure location and invalidate the test. Now we are getting into one of the most important quality control steps: eliminating contact gaps. The procedure says, apply 3% to 6% of ultimate load, then check gaps with feeler gauges. That means we apply a small seating load, not enough to crack anything, just enough to bring the beam and blocks into contact. Now here's the decision chart. Gap less than 0.10 millimeters. acceptable, proceed. Gap between 0.10 millimeters and 0.40 millimeters, correct by grinding, capping, or leather shims. Gap greater than 0.40 millimeters, correct by capping or grinding only, no shims. Notice the note. Leather shims are typically about 6 millimeters thick and full width. Technicians, this is where many labs lose accuracy. If there's a gap, the load transfers suddenly when the gap closes, and that creates shock loading and an artificial break. So we always check and correct gaps before the real loading begins.
All right, now we're at the heart of the test, loading. On the left, you see the stress versus time chart. The key message is, apply load continuously at a controlled rate. This deck highlights a typical stress rate range around 0.9 to 1.2 megapascals per minute. Now on the right is the loading rate formula. R equals S times B times D squared divided by L, where R is the loading rate, N per minute, or pounds per minute. S is the rate of increase in max stress, megapascals per minute, or PSI per minute. B is average specimen width, D is average specimen depth, L is span length. Technicians, this formula is telling you something important. The loading rate depends on specimen size. A larger beam needs a different load rate than a smaller beam to maintain the same stress rate. And the bottom instruction is simple but strict. Load continuously without shock. So no jerking the control valve, no sudden jumps, no stopping and restarting. Smooth, steady, controlled loading until failure.
Once the beam fractures, the test is not over. In fact, reporting accuracy depends on what you do next. This slide tells us timing. Measure dimensions at the fractured face after testing. So don't measure before and assume the beam is perfect. Measure after failure, where the fracture occurred. Method. Take 3 measurements for width and 3 for depth, edges and center. That means you measure width at left, center, right. Depth at left, center, right. Calculation. Use the average of the 3 for B and D. Precision. Nearest 1 millimeter. Note, if capped, include cap thickness in measurement. Technicians, this is critical. If the beam isn't perfectly uniform, and you use nominal dimensions instead of actual, your modulus of rupture will be wrong. So always measure carefully after fracture.
Now we calculate modulus of rupture when the fracture occurs in the middle third. This is what we want. The formula shown is R equals P times L divided B times D squared, where P is the maximum applied load, L is the span length, B is average width at fracture, D is average depth at fracture. It also reminds us the weight of the beam is excluded. Technicians, this is the clean, standard case. If the beam breaks in the middle third, your results are valid, and this is the calculation you use. This is why correct alignment and proper loading geometry are so important, so the fracture happens where it's supposed to happen.
Now, sometimes the beam fractures slightly outside the middle third, but still within an acceptable tolerance. This slide covers that case. It says, fracture occurs outside the middle third by less than or equal to 5% of the span length. The formula becomes R equals 3 times P times A divided by B times D squared,
where A is the average distance between the fracture line and the nearest support. Technicians, this is why you must document where the beam broke. If you just assume it broke in the middle third and use the wrong formula, your modulus of rupture will be wrong. So when you see an offset fracture, don't panic. Measure the distance, confirm it's within tolerance, and use the correct equation.
Now, this slide is the one that protects the integrity of the lab. It shows a beam with a valid region in the middle and invalid zones on the ends. The rule is simple. If the fracture occurs outside the middle third by more than 5% of span length, the test is invalid, and the instruction is bold and clear. Discard results. Technicians, this is where professionalism matters. You don't make it work. You don't round it into compliance. You don't report it anyway. If the fracture location is invalid, then the test provides no valid modulus of rupture data. The correct action is discard and retest with a new specimen if required. Quality labs protect the data, even when the result is inconvenient. Now let's talk about reporting, because a test that is not reported correctly is almost as bad as a test that was never done. This slide gives a checklist. You must report identification number, average width and depth, nearest 1 millimeter, span length, maximum applied load, modulus of rupture, nearest 0.05 megapascal, and also curing history and moisture condition, capping, grinding, shim details, specimen source, sawed or molded, and defects, age of specimen. Technicians, this is what makes results defensible. When someone questions the number, you can show the setup, the curing, the dimensions, the loading, and the specimen condition. A professional report is complete, traceable, and consistent. Let's close with precision and reliability. This is about what kind of variation we should expect. Single operator coefficient of variation, 5.7%. Acceptable difference between two tests, 16%. Multi-laboratory coefficient of variation, 7.0%. Acceptable difference between two labs, 19%. And finally, it states, bias statement. No statement on bias because there is no accepted reference standard. Technicians, this tells us that flexural testing naturally has variability. But the lab's job is to reduce variability as much as possible through discipline. And the final line summarizes exactly what controls reliability. Moisture control, apparatus geometry, gap elimination. So if you remember nothing else from today, remember this. Keep the specimen properly moist, set up the geometry precisely, eliminate gaps, and load smoothly. That's how you produce strong, reliable, defensible modulus of rupture data.